Hello everyone, and welcome to this explainer. I am absolutely thrilled you're joining me today because, honestly, we are about to embark on one of the most epic journeys imaginable. We are going to trace the grand, spectacular, and, fair warning, sometimes incredibly violent life cycle of stars. We'll follow them right from their quiet, dusty, dark beginnings all the way to their universe-shaking deaths. But here's the thing, this isn't just about looking at giant balls of burning gas billions of miles away. It's way more personal than that. We are going to uncover a profound secret today. By the end of this explainer, you are going to see exactly how your very own physical existence is deeply, intimately connected to the life and death of the cosmos. So let's get right into it.
Okay, so before we really launch into deep space, let's just establish our foundation here. When we as human beings look up at the night sky, there have generally been two different ways we interpret those patterns of light. On one side, we have astronomy. This is the rigorous scientific study of space, celestial objects, and the physical universe as a whole. Contrast this with astrology, which is a belief system that attempts to relate the positions of celestial objects to human affairs and our personality traits. Now, for our journey today, we are planting our feet firmly 100% in the realm of astronomy. While zodiac constellations might be culturally super interesting, there really isn't strong scientific evidence that they determine our futures or our personalities. So today, we'll be relying on physics, actual observation, and hard data.
And here is the roadmap for our cosmic journey today. We'll start with Section 1, Stories in the Sky. Then we'll move into Section 2, The Birth of Stars. Next up is Section 3, The Power of Fusion, followed by Section 4, Spectacular Stellar Deaths. And finally, we'll wrap it all up with Section 5, We Are Star Stuff.
Let's kick things off with Section 1, Stories in the Sky, Humanity's Celestial Connection.
You know, long before we had massive space telescopes orbiting the Earth, humanity was already deeply connected to the stars. Historically, cultures all over the globe have relied on the sky. We actually evolved from using the night sky as a giant calendar to studying it as a rigorous science. Think about the North Star, Polaris. That single point of light has been an absolutely crucial navigational anchor for sailors and travelers for centuries. We also celebrate these celestial cycles in our very own cultures. For example, in India, festivals like Makar Sankranti specifically mark the sun's movement, and Chhat Puja is entirely dedicated to worshiping the sunrise and sunset. But our understanding of what was actually happening up there deepened drastically thanks to some truly brilliant minds. You've got Aryabhata, who scientifically explained the mechanics behind eclipses, then Galileo Galilei, who took improved telescopes and turned them to the heavens, completely changing our view. Johannes Kepler came along and mathematically mapped out how planets move in orbit, and of course, Edwin Hubble, who famously proved that our Milky Way, it isn't the whole universe. There are literally countless other galaxies out there. These pioneers transformed our relationship with the sky from pure myth into profound science.
Moving right along to Section 2, The Birth of Stars, From Dust to Light. Let's look at where these things actually come from. To really understand these massive celestial bodies, we have to look at the literal wombs of the universe. Every single star out there, including our very own sun, began its life right here, in a nebula. So what is a nebula? It's an unimaginably vast cloud of gas and dust just floating in the interstellar void. We are talking about clouds that stretch across incredible distances, measured in light years. If you were inside one, it would be peaceful. It would be freezing cold, and it would just be drifting. And it's mostly made up of the most basic building blocks of the universe. We're looking at around 70 to 75% hydrogen and about 24 to 28% helium. It looks empty, but believe me, a nebula contains all the raw materials needed to ignite the cosmos.
Okay, so the big question is, how do we get from a freezing cold cloud of drifting gas to a blindingly hot, burning star? Well, gravity is the fundamental engine here. Gravity does all the heavy lifting. Sometimes there's a trigger in space, like, say, a massive shockwave from a nearby exploding star, and that shockwave causes the gas and dust in the nebula to start clumping together. It accumulates. As these clumps form, their gravitational pull naturally increases, which drags in even more material from the cloud. It snowballs. The center of this clump eventually becomes this incredibly dense, churning core. This right here is what we call a protostar. Now, hold on. Remember this detail because it's a super common trap people fall into. At this protostar stage, nuclear fusion has absolutely not started yet. It's not a true star yet. It's really just an incredibly dense, rapidly heating ball of contracting gas, and it's just sitting there, waiting for the spark.
And here is that magical spark. As gravity just relentlessly continues to crush that protostar inward, the pressure and the temperature at the very core skyrocket. Once that core temperature hits a staggering 10 million degrees, yes, 10 million, something unbelievable happens. The hydrogen atoms in the core are moving so insanely fast and are squeezed so tightly together that they literally smash into each other and fuse into helium. This is the holy grail of stellar mechanics, nuclear fusion. And because of Albert Einstein's famous equation, E=mc², we know that during this fusion, a tiny, tiny fraction of that mass is converted into a massive, frankly incomprehensible amount of outward bursting energy. The exact moment that fusion ignites, boom, a true, glowing, living star is born.
Which brings us to Section 3, the power of fusion, engines of the universe.
I really want us to pause and just try to grasp the mind-blowing scale of this nuclear fusion we just talked about. Let's consider our own sun for a second. 600 million. That is the number of tons of hydrogen our sun is converting into helium. But wait, it's not a year, it's not a day. The sun is converting 600 million tons of hydrogen into helium every single second. Every single second. Just let that wash over you. That reaction is the powerhouse, the ultimate engine, providing the exact light, heat, and radiation that makes every single living thing on Earth possible.
But how does a star not just blow itself apart with all those nuclear bombs going off in its core? Well, I want you to imagine a star as a grand, high-stakes, cosmic tug-of-war. On one side, pulling inward, you have the immense force of gravity, constantly, relentlessly trying to crush the star's mass down into a tiny little point. But on the exact opposite side, pushing outward, you have the fierce thermal pressure being generated by that nuclear fusion we just talked about. When these two massive forces perfectly, beautifully balance each other out, the star achieves a state that physicists call hydrostatic equilibrium. It's an amazing balancing act. And as long as the star has hydrogen fuel left to burn in its core, this balance keeps the star totally stable and shining bright for billions of years.
Now you might be wondering, do all stars live for the same amount of time? Absolutely not. And here is a fantastic, totally counterintuitive fact. Logically, you might think that a massive star, a star with way more fuel, would live the longest, right? A bigger gas tank means a longer road trip. Actually, scratch that. It's the exact opposite in space. Because massive stars have so much mass, they have so much more gravity crushing down on their cores. This makes their cores much hotter, which forces them to burn through their hydrogen fuel exponentially faster just to fight off gravity. So a massive star, it might only live for a few million years before burning out. It's the whole live fast, die young scenario. Meanwhile, you look at tiny stars called red dwarfs. They burn their fuel so slowly and so efficiently that they can last for trillions of years. Trillions! Our sun sits kind of comfortably in the middle of all this, with a total expected lifespan of about 10 billion years.
All right, let's move to Section 4, spectacular stellar deaths, fates sealed by mass. Because eventually the fuel always runs out. When that hydrogen fuel finally runs out, fusion stops pushing outward, and gravity finally inevitably wins that tug-of-war. But how a star dies depends entirely on how big it was. For a medium-sized star, exactly like our sun, death is actually a relatively peaceful shedding process. When the core exhausts its hydrogen, it shrinks and heats up even more, and this weirdly causes the outer layers of the star to expand massively. The star swells outward into what we call a red giant. Eventually, the star can't hold on to those outer layers anymore, and they just gently drift away into space as this beautiful, glowing cloud of gas called a planetary nebula. What's left behind right in the center? Just the naked, glowing hot core of the dead star. We call this a white dwarf. It's incredibly dense, roughly the size of our Earth, but somehow packing half the mass of our entire sun into that tiny space.
Now, there is a strict, fascinating mathematical boundary that governs these white dwarfs, and it's called the Chandrasekhar limit. Think of it as a strict rule of physics. For a white dwarf to just sit there and remain stable, its core mass absolutely cannot exceed 1.4 times the mass of our sun. That's the magic number, 1.4. If it somehow gathers more mass from a nearby star and crosses that 1.4 limit, gravity becomes way too strong for the core to support itself, the white dwarf becomes completely unstable and it will violently detonate. The universe has rules, and this limit is an absolutely critical one.
But okay, what about the heavyweights? What about stars that are just fundamentally much bigger than our sun from the very start? Well, if a star begins its life with a total mass between 8 and 25 times that of our sun, its death is not a peaceful shedding of layers. Oh no. When its fuel runs out, gravity instantly crashes the entire immense weight of that star down onto its core in literally a fraction of a second. The resulting rebound from that crash is one of the most violent, jaw-droppingly spectacular events in the entire universe, a supernova. A supernova explosion is so incredibly bright, so intensely powerful, that for a brief moment, it can actually outshine an entire galaxy of billions of stars. It's just wild to think about.
So, after the cosmic dust of a supernova clears, what's left? Again, it all comes down to mass. The leftover core's fate depends entirely on how heavy it is. If the surviving core's mass is less than 3 solar masses, gravity crushes the protons and electrons together so hard that they merge, creating a neutron star. Now, to understand how dense a neutron star is, imagine taking a sugar cube. If that single tiny sugar cube was made of neutron star material, it would weigh about 1 billion tons here on Earth. 1 billion tons for a sugar cube. However, if that leftover core is even heavier, greater than 3 solar masses, gravity wins the ultimate final victory. No physical force can stop the collapse. It collapses infinitely in on itself into a black hole. This is an object with a gravitational pull so unbelievably intense that literally nothing, not even light itself, can ever escape its grasp once it crosses the edge.
And you know, the cool thing about astronomy is that science is always uncovering new mysteries. For a really long time, it was thought that a massive supernova explosion was an absolute, non-negotiable requirement to form a black hole. But recent observations have kind of thrown a wrench in that. Astronomers found a black hole in a triple star system, meaning there's a black hole, but there are 2 other normal stars just peacefully orbiting right next to it. Now, if a massive supernova had gone off to create that black hole, those neighboring stars would have been absolutely blown away or destroyed, but they're still there. This tells astronomers something totally new. Some massive stars might undergo what's called direct collapse. They basically just fail. They bypass the supernova explosion entirely, and the whole star just directly folds in on itself to form a black hole in the dark. How eerie is that?
Okay, let's bring it all home with Section 5. We are star stuff, the cosmic connection. It is time to bring these massive, distant, mind-bending concepts right back down to Earth, right to our own daily lives. You see, these violent deaths of supermassive stars, the supernovas, they aren't just destructive events. In fact, they are the ultimate acts of cosmic creation in our universe. During the normal, everyday life of a star, nuclear fusion mostly just creates lighter elements, like helium. But during the unimaginable, extreme heat and pressure of a supermassive explosion, the universe manufactures its heavy elements. Let me put this in perspective. Look at your hand right now. Do you have a gold or silver ring on your finger? The gold, the silver, the platinum in our catalytic converters, the uranium, the lead, all of it, every single ounce, was forged in the explosive death throes of a supermassive star billions of years ago. It was blown out and scattered across the Milky Way galaxy.
And honestly, it gets even more personal than the jewelry you wear. Through a process called stellar nucleosynthesis, deep inside the boiling cores of ancient, long-dead stars, helium nuclei fused together to create carbon. When those stars eventually died, whether they gently shed their outer layers or violently exploded, they seeded the universe with that exact carbon. Over billions of years, that stardust drifted, and it eventually clumped together to form our very own solar system, our beautiful planet, and ultimately us. The carbon in your skin, the calcium in your bones, the iron in the blood pumping through your veins right at this very second, it didn't originate here on Earth. It was physically manufactured inside the fiery belly of a star billions of years before our planet even existed.
The legendary astronomer Carl Sagan once famously said, "We are made of star stuff." And it's not just a poetic metaphor, it's a literal scientific fact. We are not separate from the universe looking in. We are a direct byproduct of its most incredible, violent, and creative processes. The very atoms that make up your body right now are the recycled ancient remnants of exploded stars. So the next time you step outside and look up at the night sky, I want you to realize that you aren't just looking at cold, distant objects. You are looking at your own history. You're looking at the fiery engines that literally gave you life. So I'll leave you with this one provocative thought. If your body is currently made of the ashes of ancient dead stars, what future worlds will your atoms eventually help create?